All right, this is exam 4 for physics 102. You look at something far away and then you look at something closer. What has happened to the shape of the lens? So let's see. So if I'm looking at something far away, this is my eyeball, then I have something that's over here. So the light rays are coming in parallel and they're focusing on the retina. So the focal point is right there. But if I look at something closer, the image distance is still going to be the same, but the focal length has to get smaller, because if you consider this, the light rays will go parallel to the axis and through the focal point, and parallel to the axis. So the image is still forming on the retina, but the focal point has gotten smaller. And so the lens is going to be something like this to be something like this. It's going to be wider in the middle, so B is the right answer. Chromatic aberration is caused by wavelength dependence on the index of refraction. Object is placed at a distance of 80 centimeters from a lens along the axis. A real image forms, so that means I have a image distance of positive 40 centimeters. This, by the way, has to be a convex lens. My object is over here, my image is over here. What is the focal length of the lens? So I say 1 over P plus 1 over Q equals 1 over F. So 1 over P is 80. Plus 1 over Q, which is 40, positive 40, that's equal to 1 over F. This is 1 over 80 plus 2 over 80, that's 3 over 80, equals 1 over F, so F is equal to 80 over 3, which is 26 point something. All right, which of these best describes the image from a concave lens? Remember, a concave lens is like this, and a concave lens makes the same images as a convex mirror. So wherever my object is over here, my object is going to be here. My image is going to be here. It is a virtual diminished upright image, just like in a convex mirror. So C is right. Concave lenses and convex mirrors are both concave lenses are like this. Convex mirrors are like that, with, like a security mirror. These are both diverging devices. They cause light rays to diverge. Both of these do. Like that. Which of these rays is drawn incorrectly? Let's see. What's this, C? Ray C goes parallel to the axis through the focal point. That one's all right, so I get rid of those. This is A right here, goes through the focal point and parallel to the axis, so A is right. And B, looks like it just sort of goes somewhere and then it goes parallel to the axis, so B is not correct. Two waves of wavelength 4 meters travel through space. The first wave travels 8 meters, the second wave travels 12 meters. So our path length difference then is 12 minus 8, which is equal to 4 meters. So these waves have traveled a path length difference equivalent to 1 wavelength. So it's like if I have a wave like this, and then my next wave starts 1 wavelength away. I see that's not very good. My peaks and peaks are going to line up, my troughs and troughs are going to line up. So that's constructive interference. Consider this two-lens system. What is the final magnification? All right, well, this is P1, F1, so I get 1 over F1, that's 10, equals 1 over P1, that's 1 over 20, plus 1 over Q1. I solve that for Q1, and it's equal to 10. And then M1 is equal to negative Q1, negative Q1, which is 10, divided by, I'm sorry, this isn't 10, this is 20 right here. Sorry about that. So it's negative 20, that's Q1, divided by 20, that's P, and so that's going to be negative 1. Now we do the exact same thing. So my image is 20 centimeters to the right, same size as the object but inverted. That means this distance is 30 centimeters. And so I get 1 over 15, that's the focal length, equals 1 over P, that's 1 over 30, plus 1 over Q. That's 2 over 30, so minus 1 over 30, the inverse, so Q is equal to 30 centimeters. And so M2 is equal to negative 30, negative Q, divided by P, which is also 30, so it's also negative 1. Negative 1 times negative 1 is positive 1. So 8 is D. Laser beam is incident on 2 slits that are 0.1 millimeters apart. How far is the second bright fringe? So let's just write down the things that we know. I know wavelength is 650 times 10 to the minus 9. meters. The distance between the slits is 0.1 times 10 to the minus 3, and m is the second order, so m is equal to 2, and then L, that's the distance to the screen, is 5 meters. So first I say d sine theta equals m lambda. So theta is the inverse sine of m lambda over d using those values. Inverse sine of m lambda over d. That's 2 times 650 times 10 to the minus 9. D is 0.1 to the minus 3. Inverse sine of that, I get 0.745 degrees. And then I say, well, y is equal to L tan theta. Times 5. That's equal to 6.5 times 10 to the minus 2 meters, which is 6.5 centimeters. Young's double slit apparatus, what factors the distance between the adjacent light and dark fringes when the wavelength is doubled? So d sine theta equals m lambda. If I double this, I double this, and that sine theta term, and then y equals L tan theta. If sine theta is doubled, this is also doubled, so the distance between the light and dark fringes is also doubled. So B is the right answer for number 10. Okay, I have a double slit experiment. Which of these scenarios will occur? Okay, it's not two vertical bands of light, though that seems like what it should be. It's not one very bright vertical band of light surrounded by never-ending dark bands on either side. They actually will come to an end, so we can get rid of that. And it's definitely not going to be the screen uniformly illuminated. It's going to be A. What is the highest order maximum? So whenever we see that, we think 90 degrees is equal to theta. That's the highest order that I can get for a diffraction grating for a double slit or for a single slit. This is for a grating, a diffraction grating. So I say d sine theta equals m lambda. I'm solving this for m. Sine of 90 is 1, so it's just going to be d divided by lambda. So that's 4 times 10 to the minus 6 divided by 600 times 10 to the minus 9. I get 6.7. So the highest order that I get is the 6th order. You don't round up because you can't go above 6.7. Here I have 3,000 lines per centimeter. What's the slit spacing? So I just say 1 over 3,000. That'll give me the number of centimeters per line. And that is 3.3 times 10 to the minus 4. But this is in centimeters per line. I want it in meters, so I'll move that decimal place over 2 places. Diffraction grating has 10,000 lines per centimeter. How many bright spots are on the screen? So think about the number of bright spots. Actually, let's calculate M first. We'll need to do that. So first, I should calculate D, 1 over 10,000. That's in centimeters, so it's going to be 1 times 10 to the minus 6 meters is D. D sine theta is equal to m lambda. Just like we had before, this is going to be 90 degrees because we're looking for the maximum number of spots, so that sine of 90 is equal to 1. So m is just equal to d divided by lambda. So that's 1 times 10 to the minus 6. Divided by the wavelength, which is 312 times 10 to the minus 9. I get 3.2. That means I'm going to get 3 orders. I'm going to get m equal 1, 2, and 3, and then m equals 0. So the total number of dark spots on the screen, or bright spots on the screen, is going to be 7. I have the central bright fringe, and I have 3 on each side. Single slit experiment, what path length difference gives us this? That's going to be 1 wavelength. I use a single slit to create an interference pattern. If I increase the wavelength, what happens to the width of the central bright fringe? Well, d sine theta equals m lambda. If I increase the wavelength, this increases the angle theta. So if I increase the wavelength, it'll get wider. We've had a similar question to that. Sorry. Speed of the wave depends on which of these? Speed of the wave only depends on the medium, so C is right. Which has the higher frequency? This one, A. Sound has an intensity of 2 watts per square meter. You increase the intensity so that its intensity level, that's the number of decibels, increases by 3 decibels. So I use this expression, I1 over I2 equals let's see, I always forget. Let's just take a quick look at our equation sheet. Where is it? Well, it's not there. I'll have to include it, but it's the 10 to the delta L over 10. I'm going to check that. Give me just a second. Yeah, that's right. So here, I1 is 2 over I2, and that's equal to the 10 to the 3 over 10. 10 to the 0.3 is equal to 2. I'm sorry, I got this backwards. Excuse me. Sorry about that. This should be I2 over I1. This doesn't work out right. So here I'm going to have I2 over this. So I2 over 2. That's my I1. I2 over 2 is equal to 2. And so I2 is equal to 4 watts per square meter. I know I'm increasing my intensity level, so it has to get louder. It has to be more intense. And it is. It's at 4 watts per square meter. So 19 is a 50 decibels is how many times as intense? Well, it's an increase of 30 dB, and so that's 1,000 times as intense. 2 tones are played on a guitar. One is 130, one is 128. The beat frequency is 2 hertz. Wah, 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 wah. The length of a guitar string is increased by a factor of 2. By what factor does its frequency change? Well, the frequency is dependent on 1 over 2L square root of T over mu. And so if I increase the length by a factor of 2, that means the frequency has to decrease by a factor of 2. So it's going to be B is 22. So the standing wave, if the length of the string is 6 meters, what is the wavelength? Well, the wavelength goes from here to here. So it's going to be 2/3 of 6, which is 4 meters. 4 meters. Points on the end of the string, those are called nodes. That's these points right here where the wave doesn't move up and down. Which of these is called the ear canal? That's 2. Which part acts as a lever? Those are your ossicles. That's number 3. And a vibrating string has a frequency of 320. What if you increase the tension in the string by a factor of 2? So going back to what we had before, 1 over 2L square root of T over mu. That T is the tension. What if I double it? Then I'm going to increase my frequency by a factor of root 2. So let's say 320 times the square root of 2, which is 1.4, and I get 450 hertz. I know that it has to get bigger, right? So I can get rid of this, this, and this. So it's either A or E. And then my favorite class, I think my favorite class is this class, in fact. So it's been a good class this semester. I appreciate y'all.